Sir Isaac Newton, when he was a very young man, there was a plague in London. The bubonic plague was sweeping through London, and so what people of means did is they got out of the city and they went out to the farm, the family farm, and he didn't like to do manual labor. So instead, he sat in his room, and over the next 2 years, he invented physics. And while he was at it, he invented calculus. Truly one of the greatest, most productive periods of time in the history of science by a single individual. So we're going to learn a little bit of what he did in that period of time. And it's called Newton's laws. These are really Newton's laws of motion. He also has other laws of gravity and light and so on, but we're going to talk about his laws of motion. And there's 3 of them. And the first one we call the law of inertia. And the law of inertia is actually pretty easy to understand. And if I have a baseball, I know that if I just leave the baseball here, the baseball is just going to sit here, and no matter, it's going to take it's not going to do anything. Why? Why doesn't it just fly off on its own? Because it has inertia. But, can you close the door? So it's at rest, and it's just going to stay at rest unless some outside agent goes boink, applies a force to it. Another idea is that if I throw this baseball, it will eventually rattle around, hit, and run into things and come to a stop. But what if I was out in space and there was nothing in my way, or in the ball's way? Then if I threw the ball, it would just keep going, wouldn't it? I mean, it would just keep going forever. And if it was in outer space, it would just go, in a straight line forever. It's easy for us because we've been educated about the nature of the solar system and the universe to imagine that. It was almost impossible to imagine in the time of Galileo and Newton, because everything they saw in motion eventually came to rest. So they just imagined that the natural state of all things were to be at rest. But that's not the natural state of all things. Objects will remain at rest. If they start off at rest, they will remain in motion unless acted upon by an outside force. And that's the law of inertia. It was really an idea that Galileo came up with, but Newton generalized. And so it's one of, even though Galileo kind of created this idea, Newton gets credit for it as one of his 3 laws. The second law is the law of acceleration. We've been dealing with acceleration now for a couple weeks, or actually a month. But we've never really talked about what causes an object to accelerate. It's a force. And Newton formalized how forces and accelerations are related. And the law of acceleration is most easily described by an equation. If I have a car and I want this car to accelerate, I have to push on the car with a force. Okay? And it can be experimentally verified that the amount of push or pull I put on that car will cause the car to accelerate. And if I double the force, I double the acceleration. So the force and the acceleration are directly related mathematically. But of course, some things are easier to push than others. Like I have this little toy, and it doesn't weigh very much. But I have this thing, and it's metal, and it's very dense, and oh, this thing is hard to move around. It's hard to accelerate this thing. So some things are easy to accelerate, like my pencil here. Whew, oh, nothing. So easy. This is so easy. You should try it. It's really easy. This, oh my gosh. This is so hard. All right, enough. The harder it is, the hardness of it is to accelerate an object. We have a name for that. We call it inertia. This has more inertia than this. This has, how much inertia does this have? Well, this has 1 kilogram of inertia. I don't know what this is. It's probably a few grams. My pencil. But, oh, so hard. Now, we have a name for inertia. We have another name for inertia. We call it mass. So this is force. This is mass. And this is acceleration. F equals ma. This is a vector equation. Obviously, a push or a pull, here's a push, and here's a pull. It has direction associated with it. So it is a vector. Acceleration is a vector. Mass is not a vector. I would not say this object has 1 kilogram of mass to the east. Okay, that would make no sense whatsoever. It's a scalar quantity. In chemistry, you learn about mass. You're told that it's a measure of how much matter is in a thing. And that's true. In physics, though, we describe mass as how hard it is to accelerate an object. Now, by the way, I'm feeling this thing, and it's kind of heavy. Okay, what I'm feeling is the force of gravity. I'm not feeling its mass when I do this. Now, this is a really important point. Everybody pay attention to this. If I hold it right here, it's pushing down on my hand. If I went to the moon, it wouldn't feel nearly as heavy. It would feel 1/6 as heavy. And if I was on the International Space Station in free fall around the Earth, and I put this thing on the thing, this thing would just drift off my hand slowly. I mean, it wouldn't weigh anything. Weight is not mass. Now, if I were to take this thing to the moon, or into space, or here on Earth, and I move it sideways like this, and I feel the resistance to my changing its direction and velocity, it would feel the same. If I was in zero gravity environment, and I just grabbed this thing, and I just wiggled it around, it would feel the same as it does right here on Earth, except it doesn't have the downward pull of gravity, but its resistance to to acceleration, I would feel it. It would feel exactly the same. Mass doesn't depend on gravity. Mass is a measure of how much resistance it has to acceleration, which is a measure of how much stuff it has, which is what you learn in chemistry. This is the most important equation in all of physics. You've heard other equations that are famous, like E equals mc squared. Really important equation. But in terms of practical use, when Newton came up with this and published his results, it's no coincidence that right after this equation got published, the Industrial Revolution soon started. Because this little equation allows me to understand how objects move under forces. It allows me to do, or allowed humans to do, engineering. It's the fundamental equation of engineering, as well as studying anything that's moving through space. The third law is the law of interaction. Now, I was a little older than you when I studied physics, calculus-based physics for the first time. I was a freshman in college. And I remember the frustrations of trying to solve those horrible relative velocity problems. And I remember getting so mad that I actually punched a wall. Now, some of you, we all handle physics grief differently. Some of us cry. Some of us, we don't want to cry because, we suffer from testosterone poisoning. So we decide instead to viciously lash out at inanimate objects, like our textbooks, throwing them against the wall or punching the wall. Okay, and we soon discover the law of interaction. Because what this says is that for every force, and I'm going to write this one out. This one, law of inertia, you just read. But this one, for every force, there exists another force. Oh, wait. Sorry. I left something out. For every force, on an object, there exists an equal but opposite in direction force on another object. Okay, sorry. I like to try to phrase these in ways that are a little more understandable. I'm trying anyway. Now, what that means is that when I punch the wall, here's a wall, and here's my fist. Don't try to draw a fist. That never really, I don't know. Here's my, oh God, that's terrible. Here's my fist. I'll just make it a big thing. Okay. Bam! Right, here's the wall. Bam! I'm hitting the wall with my fist. So I'm going to apply a big, huge force on the wall. But I will soon discover, and you can try it right now if you want. The walls are pretty hard. You can't really hurt them. The wall applies an equal and opposite force to my hand. The wall is relatively unaffected by this force. My hand is, maybe literally destroyed by the equal and opposite force applied to it. Every force, there is an equal and opposite interaction force. They call it actions and reactions sometimes. But for every force on one object, there exists an equal and opposite force on another object. Always. Always, always, always. There's no exception to this. No exception to this, no exception to this. These are laws of nature, which means in all our observations of nature, we've never observed a contradiction. This is the way it is, the way the universe works. So, if we have two objects that are interacting, we can say this is the, let's call this, the wall is object 1 and my fist is object 2. The force of 1 on 2, see the subscript there, 1 on 2, will be equal, but in the opposite direction of the force of 2 on 1. Now, I normally drop the ons. Everywhere in the universe. The question was, is this true in space? This is true everywhere that we have observed. We have never observed this not to be true. This turns out to be, all three of these are extremely important. These are actually pretty simple ideas, I think. I mean, it's pretty obvious that objects don't move unless you push on them. And once you do push on them, the only way they can stop is for something else to push on them, right? This one is a little tough but we can derive it empirically. But and this one, we have some experience with that. That punching a wall is a good example. But using these ideas is challenging, as you're going to discover. Now let's talk about units now. In the metric system, we use this equation to find the units for force. So we have a force is equal to mass times acceleration. Well, we have a unit of mass in the metric system called the kilogram. And then we have a unit of the metric units for acceleration, which we've already dealt with, meters per second squared. And we collect these units together and we call them newtons. And we abbreviate it with a capital N. Yes?
Question about the force of mass and acceleration equation. Now, if you had an object going at a constant velocity, wouldn't it have no acceleration?
Yes.
And then your force, basically the equation would be 0?
Yeah. The question was, if an object is moving with constant velocity, that means so what does that mean in terms of force? It means there's no net force on the object. Now there can be forces on the object, but when I add all those forces together, they will equal 0. So one of the things I should have I'll add to that is I'll call this the net force. It's almost like you asked that, like I paid you to ask that question, Patrick, because this isn't. I can have more than one force acting on an object. Maybe they'll add up. Maybe they'll cancel out. Whatever remains after you add add them all together is your net force, and that net force will cause an object to accelerate. Now, for example, if you're driving down the road, and here's your car. Oh, look at that fancy car. And you're driving down the road. Hold on. So this car's got a constant velocity. Now let's look at all the forces that are acting on this car. Gravity's pulling it down. The ground is pushing it up. We have wind resistance. The wheels are applying a force, trying to pull it forward. There's all kinds of forces, and this is what we're going to study. But if your velocity is constant, that means your acceleration is 0, which means there is no net force on the car. That means when I add up all the forces, they'll be equal to 0. We're going to study that in depth. Because now there's a way of expressing that. I'm almost done. And that is, well, let's do a simple problem. Let's do this with an example. I've got a little cart on wheels here. And let's say this cart has 10 kilograms. And let's say someone is pulling on it with 50 newtons of force. Now 50 newtons, by the way, just divide that by 5. It's about 10 pounds, maybe a little more. It's the conversion factor from pounds to newtons. 1 pound is equal to 4.45 newtons. But this object, look, you pull on this, there's wheels, and all, it's going to accelerate. And you can say, well, we're pulling on it with 50 newtons of force, so you can say F equals ma. So A is equal to the force, 50 newtons, divided by the mass, 10 kilograms. It's going to accelerate with 5 meters per second every second, or meters per second squared. So look, if I tell you what the force is going to be, I can tell you what the acceleration is going to be. But what if somebody is pulling the other way? Like this, with, let's say, 30 newtons of force. Well, now you have to add these together. So really, Newton's second law can be written like this. We have a way of saying add them all together. It's a summation sign. Some people freak out by notation in mathematics, but don't freak out. You've seen this before. The summation sign? Well, if you haven't, don't worry about it. This just means, hey, add up all the forces. So here I would do this. I would say 50 newtons plus, but this is in the opposite direction, in the negative direction, so I'll say plus negative 30 newtons equals ma. So what's the acceleration? Well, it's going to be 50 minus 30 is 20 newtons divided by 10 kilograms. That will accelerate at 2 meters per second every second. And doesn't that make sense? If all you've got is the 50 Newton force, there it goes. But if you pull backwards on it, you're going to have less overall force to cause the acceleration. Finally, I want to talk about weight, because they do talk about weight in here. One of Newton's laws is the law of gravity, and we're going to cover that in a little while. Forget which chapter. But if I, like my little, here's my 1 kilogram mass, so I'll just draw a picture of it like this. Massive objects, turns out that they distort the space-time around them in such a way that they are attracted to each other. Earth wants to pull this massive object down. Now we know this. I can feel it. The Earth is pulling this thing down. What you might not know is that this object is pulling up on the Earth with an equal and opposite force. Yes, this 1 kilogram mass is pulling the Earth up towards it. How come I don't see the Earth just suddenly slamming upwards towards this mass when I hold it up? Because the Earth has a mass of 5.98 times 10 to the 24 kilograms. It's big. This is little. So the effect of this force is negligible. We don't even see it. We can't even notice it. The force of this, pretty significant. It's going to fall down. So the force due to gravity is equal to the mass times the acceleration due to gravity. And we're going to actually do a little lab on this, and we're going to figure this out. But it is in the book, and it's one of the problems that you'll have to do. Now, the last part of the book here, 5.6, the last chapter, you are going to have to read it. I'm running out of time, so I'm not going to have time to go over it. But it is going to be part of the lecture for section 5.7 anyway. The interaction diagram. But read it. Hey, read the book thoroughly. Take notes on the book. Look at what I did here, and then do the problems for assignment. Yes.